So we're looking at the bottom of page 9, and then we'll get on to page 10 in a minute of the Unit P packet. We're talking about the method for finding an angle of rotation for a given conic. So the process is it's pretty straightforward, but there's a long story as to why everything works the way it does. So the first thing you do is you put the conic in general form, specifically or particularly in rectangular form. Use this formula. All right. And so that actually is the rule to solve for the angle of rotation. There's other methods. There's a matrix-related approach, but this is a pretty user-friendly way of doing it, especially since oftentimes the the information will be given to you in the general form. So it kind of lends itself to this approach. So let's hop on over to page 10 and take a look at an example. All right. It looks like I typed one of them in already. Well, something close to one of them. So determine the angle that each ellipse would have to be rotated to be in standard position. So basically it's saying find the angle of rotation. All right, so we're working with this formula, but you might look at it and say, well, I don't see no A, B's, and C's. So just remember or know that it's ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. That's the general form. All right. With the bxy indicating that there's some sort of rotation going on. All right. So the idea there being that if there was no rotation, that would just zero out. So the b value, and you just kind of, like old school quadratic formula thinking, you identify your a, b, and c values. A, b, and c. A would be 13, b would be 6 radical 3, and c would be the 7. All right, so we're talking 1/2 inverse tangent of 6 radical 3 over 13 minus 7. So 1/2 inverse tangent. Now inverse tangent has a domain that exists in the interval of negative pi over 2 to pi over 2. So we have to keep that in mind. All right, so you got to know your inverse tangent relationships. All right, which kind of makes sense because once you start getting into rotations that are beyond 90 degrees in either direction, then odds are you're picking up a rotation with something that could be determined using an acute angle. All right, but either way, we're looking at a radical 3. All right, so based off of your ASTC business, you're thinking old school trig. We're talking a domain that only is going to exist. Look, that was supposed to highlight. Somebody did not get the memo. There it is. We're only living in this interval. So negative pi over 2. Here's negative pi over 2. And here's pi over 2. Alright, let me just kind of give myself some more room. I have the space, why not use it? Alright, so since this is a positive ratio, I know that I must be in the first quadrant there. Alright, so if you know your inverse trig rules, basically your unit circle rules, then you would know that this corresponds to a 60-degree angle. All right, so 60 degrees. Or you can, if you want, you can go in radian form. For this kind of stuff, it really doesn't matter. It's 1/2 of that, so it's a 30-degree rotation. All right, you should expect more often than not to have results that are going to end up being unit circle values. All right, so take a quick look. 13x squared plus 6 radical 3 xy plus 7y squared minus 64 equals 0. All right, so we're looking at, just get that going there. Yeah, it's kind of hard to see, but it looks like it could be a 30-degree rotation. At first glance, it looked like, I was like, oh, where did I go wrong? But assuming that it was a vertically oriented ellipse to begin with, that would make sense, right? So, just kind of imagine that middle term there was, it was some conglomeration of x's and y's. But if this were a vertically organized ellipse, then it would be something that seems to be rotated just by a measure of 30 degrees. All right, so I want to see if I can illustrate that really quickly for you. Let me do y equals, the slope would be, if it's a 30-degree angle in the second, actually it would be a 60-degree reference angle, so that would be negative 1/2 radical 3 over 2. So change in y or change in x. Negative radical 3. And then x. Yeah. Just going through the origin. So this would be a 30-degree rotation off of the y-axis. And I'll just illustrate the y-axis. I mean, you know what the y-axis looks like, but I'll just emphasize it. All right, so blue line to red line. That rotation there is what would have led to that new ellipse. So if the original ellipse was vertically organized, so like taller than it was wide, then that would correspond with a 30-degree rotation. So we're kind of flying blind here in the sense that we didn't really investigate what this original ellipse would be without any kind of rotation. But now we kind of have the sense. If we unrotate this, yeah, it would play out the right way. So I'm gonna snag this graph because that's my my MO is to, wherever possible, especially if it's something in the realm of more complicated in terms of graphs, let Desmos do the work for you. Boom. No reason you should have to make that on your own. All right, so the next one, same idea. Oh, I already pasted it. So we're looking at phi, or call it phi. It's more like a delta. So phi would be equal to 1/2 inverse tangent. The b value is 6. A minus c, so 5 minus 5. All right, so that would be equal to 6 over 0. That's undefined. All right, so that doesn't mean no solution when it comes to tangents. So tangent, inverse tangent of 6 over 0. All it means is we got to be thinking about where tangent is undefined. Well, tangent is undefined wherever cosine is equal to 0. So it's going to be a y-axis value. All right, so we're talking about a 90-degree rotation here. All right, so this part would be 90 degrees. All right, so we're looking at 1/2 of 90, which is going to be 45 degrees. It's just a question of which direction, right? Because we don't, how do you don't say negative undefined. There's two instances in which the tangent function is undefined, here and here. So in the direction of negative pi over 2, but also pi over 2. So that's where Desmos becomes a useful resource, because if you have an idea of what the figure would look like going in, or you can kind of infer what it would look like, then you can draw a reasonable conclusion. So let's take a look. All right, so that's what we got. And if I were to plot a 45-degree angle, that would be really y equals negative x. Not y equals negative y equals negative x. That's a 45-degree angle. So you could actually make a case that this was a wide ellipse that was rotated in the negative direction, or it was a tall ellipse that was rotated in the positive direction. Either way, you can make a case. All right. So, but the bottom line is that it was rotated 45 degrees, and that's really all we care about. All right. Because as we move forward, you're going to see why we're talking about all this stuff. And it isn't so much the idea that you learn how to create the graphs as it is that you know how to unrotate so that you can do all your evaluations as a oh, that was fun. I didn't even know that could do that. You can do all your calculus to the ellipse in its ordinary unrotated standard form, which makes everybody's life a lot easier. So it's kind of like it starts off rotated, so you unrotate it, do all your calculus, and then rotate it back. All right, so that's more on that later, but that's kind of the gist of it. All right. In this case, in number 5, it looks like we have the same coefficients. So I'm going to just do a copy paste job here. Except the b value is now negative. All right, so it's still going to be a 45-degree movement. It's just a question of which direction. All right. So it's just going the other way. All right, but it's still a 45-degree movement. Now again, depending on, and now it's tricky because since this is a 45-degree movement, it could have been a case where you had, like I was saying before, you could have had an ellipse that looked like this, that got rotated that away, or you could have had an ellipse that looked like this and rotated that away. All right, but that's only because it's 45 degrees. If it's like 30 degrees or 20 degrees or 5 degrees or something like that, it becomes a little bit more obvious. All right, but in this case, we're looking at this sort of figure. All right, but it is still a 45-degree movement. All right, so the direction is a limited cross-product term by determining an angle of rotation between 0 and 90 degrees. And again, that's all we're looking for. We're just trying to make a determination of what the correct angle of rotation would be. All right, and then the next one. The b term, 90 radical 3, a minus c, 151 minus 61. That's 90 over 90, so another radical 3. So we're looking at a 30-degree rotation. All right. Now these problems are actually asking us to do a little bit more, but I'm just going to amend that now, and say that we're just trying to find the angle of rotation, determine the angle of rotation, because doing a conversion would really, I mean, it's beyond really the scope. This is an old pre-calc lesson. It's beyond the scope of what we're going to be doing here, because we're going to be doing a lot of stuff in parametric form and polar form and such. So there isn't really much of a need to go down this road. All right, so this is really what the amended directions will be. I'll change it in the master notes, but at least for this video, that's what the